Hello and welcome back to Monroe Tutoring, or if it's your first time, just welcome. We're going to talk about both electron and molecular geometry today. I didn't write electron here, let me jot that in. But the point is, these two things are completely intertwined, right? Is electron geometry and molecular geometry. And so let's just jump right in and start with an example. And so I'm going to give the example of methane. And of course, this lecture is building off of my lecture on Lewis structures, and formal charges isn't really as important for this particular one. But the Lewis structures one, you have to know how to do Lewis structures in order to understand molecular geometry. So if I draw the structure of something, the Lewis structure, let's do methane, which is CH4, and it is just a carbon bonded to 4 hydrogens as such. And if we just look at the Lewis structure, because we have to represent it in 2 dimensions on a piece of paper or on a board like this, the point is it looks kind of like a cross shape, right? Like a T, but of course, in reality, it does not have that shape. And so let's understand why that is. So the first thing in my chart here is how many electron regions does this have? And a bond or an atom bonded to the central atom is an electron region. So this carbon has 4 atoms bonded to it, so it has 4 electron regions. Because remember, the electrons are on the outside of an atom, the protons and neutrons are on the nucleus in the center. And so basically you have an electron-rich region over here where the electrons are whizzing around, right? You have the valence electrons participating in these covalent bonds. And so we kind of have these 4 electron clouds that are between the nucleus of the carbon and the nucleus of the hydrogen atoms. And of course, we're just talking about the valence electrons here. But the point is, there are 4 electron regions here. And there are no lone pairs on the central atom. And so this LP is central lone pairs, there's 0, okay? So this is going to give us like the pure geometry of a shape that has 4 electron regions. When all 4 electron regions are atoms that are bonded to the central atom and not lone pairs, we have, well, it's like I said, it's the pure one. So the electron geometry is called tetrahedral. And let me write that in, and then I'll explain this as we go here. Tetrahedral. And tetrahedral, tetra is like the prefix for 4, right? And so the electron geometry is tetrahedral. And what does that mean? If you took 4 things that are negatively charged, which, you know, the outer clouds here of the attached atoms are negatively charged, they're going to repel each other. And they want to get as far away from each other as they can. And so if you just had 4 negative things on strings and you tied them all in a knot in the middle, and they're trying to repel each other and get away from each other, they're going to form what's called a tetrahedron, or this tetrahedral shape. And what that is something like this, right? It's not a T as we see on the page here with like 90 degrees in between each of these, because if we look at that, from this hydrogen to this hydrogen, if it really was flat, would be 180 degrees. So there's wasted space where these things can get further away from each other. A tetrahedron is kind of like a pyramid. It's like a 3-sided pyramid, but with another group sticking up out of that. And so if you take this and you flop it over onto one of the sides, you get the same shape back, right? It's completely symmetrical. It's like a 3-sided pyramid base with one group sticking up. And no matter which way you flip it, you always end up with that same thing, a 3-sided pyramid with one thing sticking up. And so because the electron geometry is tetrahedral and all the electron groups are atoms bonded to the central atom, the molecular geometry is also tetrahedral. It's the same thing, right? Because all 4 electron groups are atoms bonded to the central atom. So electron geometry and molecular geometry are both tetrahedral. This will make more sense as I continue doing the examples here. So just bear with me for a moment, okay? So electron geometry and molecular geometry are both tetrahedral. And the bond angles, if you take any of these 2 atoms here, right, any 2 atoms that are close to each other, that angle between them is 109.5 degrees. And, you know, it's just, if you take 4 things and stick them together and they want to get away from each other as far as they can, they form this shape naturally, and that's the angle that you get if you measured it. Now, let's continue here. What if I had another atom that's very similar to, another molecule rather, that's very similar to this, but we replace one of the bonded atoms to the central atom with a lone pair. So let's do ammonia. If we take NH3, it's a nitrogen bonded to 3 hydrogens. And I could have did NF3, but I just want to make this as simple as possible. How many electron regions does this have? Well, there's 3 atoms bonded and a lone pair. The lone pair is just an electron cloud floating around, right? And the atoms bonded also have electron clouds, right? So the exterior of the atoms that are bonded are negatively charged, and the lone pair just is completely negatively charged, right? It's just a cloud of electrons. So they still are all repelling each other just like they do here. There's still 4 electron regions because those 2 electrons in the lone pair occupy one of the molecular orbitals. And so we still have 4 electron regions, but this time we have 1 lone pair. And I could have thrown in another column titled quantity of atoms bonded to the central atom, which in this case would be 3. And then the number of atoms bonded to the central atom plus the number of lone pairs on the central atom add up to the number of electron regions. So the electron geometry is still going to be tetrahedral because the furthest thing that 4 negatively charged groups can get away from each other is making this tetrahedral shape. So we still get tetrahedral. I'm just going to do a double quote here because it's the same. But the molecular geometry is kind of like this, but the lone pair, we can think of it kind of like an invisible atom. And so if I just pop one of these atoms out, I end up with this shape, right? And so this shape is what we call trigonal because there's 3 atoms, 3 things is trigonal, and then it's pyramidal because it forms a bit of a pyramidal shape. And so the electron geometry and the molecular geometry differ when you have some lone pairs. And so over here, we're going to call this, I'm just going to abbreviate trigonal. Actually, no, I lied. I'm going to write it out because I haven't written it out yet. So it's trigonal, and that's pyramidal. Pyramidal. And so we would expect the bond angles to possibly be about the 109.5, but the thing is that the lone pair, because that's an electron cloud that does not have a positive nucleus, its effective negative charge is stronger, right? Because if we look at the atoms bonded, this is a positive proton with electrons whizzing around the outside, so the effective negative charge is not really a -1, right? The negatives are on the outside, but there is a positive in the center, kind of diminishing the full effect of that negative charge. But the lone pair, that's just 2 electrons. So that lone pair repels the other atoms a bit more strongly because it's a stronger negative area, a negative region. So the electron region of a lone pair pushes harder than the electron regions of bonded atoms. And what that does is it kind of squeezes the atoms a little closer together. And so the bond angles in trigonal pyramidal are not quite 109.5, they're a little less. And so it does depend on what the atoms bonded to the central atom are. Are they huge atoms with a boatload of electrons, or are they little atoms like hydrogen that only has 1 valence electron? So we can't give a specific number for this shape in general, trigonal pyramidal, but what we can say is that it's going to be less than 109.5 degrees. I think in the case of NH3, it's about 107 degrees approximately. But again, if I replace the hydrogens with like chlorines or bromines, then it may not be quite as much of a drastic push on them to squeeze them together, because if the atoms are really large, then they're going to kind of, run into a place where they can't be squeezed that close together. So without overcomplicating this, the point is when we have 4 electron regions, we have the tetrahedral electron geometry. Molecular geometry is trigonal pyramidal if we have a lone pair replacing one of the atoms. And the bond angle is going to be a little bit less than the pure tetrahedral bond angle. So I'm just going to write less than 109.5 degrees. And of course, this is just the less than symbol, right? So let's keep going here. And let's say, let's do water. So we have H bonded to an O, bonded to an H, 2 lone pairs. This is a classic one to get wrong. Because when we look at what we drew here, it looks like this is linear, right? We have the H, a straight line, the O, and a straight line, the next H. And that just looks like the thing is a straight line, which would be linear. But we have to look at how many electron regions are on the central atom. And so there's 2 atoms bonded and 2 lone pairs on the oxygen. So there's 4 electron regions on this central atom. So I'm going to write over here, we have the 4. And then for lone pairs, there's 2 lone pairs on the central atom. Now, because there's 4 electron regions, of course, the electron geometry is again going to be tetrahedral. So I'm just going to put my double quotes here. And now the thing is, if we have a shape that starts off as tetrahedral, but then 2 of the atoms or 2 of the electron regions are kind of like the invisible force of a lone pair, because they have the same push, if not stronger than another atom bonded, but you know, it's like an invisible atom taking up space, but it's not an atom, right? And so if we pull these out, look at what shape we get. We end up with a bent structure. You have an angle. It's not going to be linear like we draw it on the page. It's going to have this type of shape because the other 2 lone pairs are taking up physical space, or they're repelling the atoms out of those areas. Yet we, you know, when we look at the actual molecular geometry, they don't counter in, right? It's not like it's just tetrahedral with 4 atoms bonded. It's the tetrahedral electron geometry, but yet what does this look? Just bent, okay? So the molecular geometry of water, or of anything like this, that's tetrahedral electron geometry, but only 2 atoms bonded to the central atom, is going to be bent. And then in the case of water, the bond angle is roughly like 105 degrees, I believe. But again, if these were bromines or something, it's going to have a different angle. So we just say less than 109.5 degrees. Less than 109.5 degrees. And those are basically the shapes that we're going to get from the electron geometry of tetrahedral. So 4 electron regions. So now let's continue and let's do another example, but we're going to start off with a different number of initial electron regions. So here's my eraser. Let's go make up another example here. And while I'm doing that, guys, if these videos help you, please give it a like, follow, subscribe, share this video with someone else that could use the lessons. And if you'd really like to support the channel above and beyond, please check me out over here, and you can patronize me. That helps me to continue making these videos for free, as well as, you know, commenting. You can ask any questions that you have, or if you just want to drop in and say hi, that's welcomed as well. All those things help out the algorithm and help the channel out. So let's now think about an example that's only going to have 3 electron regions, and our first example should have all 3 electron regions being an atom. Okay, so off the top of my head, I'm thinking of nitrate ion, like I did in my Lewis structure video. So let's just do that. Or actually, no. Let's change it up a bit. Let's just do like BH3. This way, we're not drawing charges or double bonds or anything right now. But it doesn't really matter. It's the same idea. So over here, if we have BH3, there are only 3 electron regions because there's 3 atoms bonded to the central atom and there's no lone pairs, right? An atom bonded to the central atom and a lone pair are both considered an electron region. So this has 3 electron regions, no lone pairs. So since there's 3 atoms bonded, we're going to have trigonal again. But trigonal, and then the second word is going to describe the actual geometry here. The furthest that 3 things can get away from each other is going to be basically how I drew it on the page, which is trigonal planar. And so, by the way, you can actually do this. If you tied 3 balloons to each other and they're all blown up, they're going to make this shape. If you tied 4 balloons to each other, they're going to make the tetrahedral shape. So trigonal planar is the electron geometry here, and it's planar because it's flat. It's trigonal because there's 3 atoms bonded to the central atom. So I'm not going to write out trigonal this time. I'm just going to write trig and then planar. I already wrote out trigonal before. So because all the electron regions are atoms, the molecular geometry is the same as the electron geometry. So this is also trig planar. And then if you just took a circle 360 degrees and divide into 3 spots, that's 120 degrees between any of these outer atoms. So that is 120 degrees. Now, what if I have the same idea, but I take away one of the atoms? So let's do something like, let's see, I want to have like a lone pair, and I want to have, let's do something like HNO is a good one. If I do HNO, I have H to the N, to an O, and there's a lone pair in the nitrogen, okay? And so here, again, if you just draw it on the page, it looks linear. That's a very natural pitfall to fall into here, right? Because it looks linear, but you have to check how many electron regions does it have. And it has, there's 1 atom here, 1 atom there, and the lone pair all on the central atom. Lone pairs on outer atoms do not affect this. We're talking about the geometry of the central atom. And so there's 3 electron regions. One of those regions is a lone pair. And so the electron geometry, since there's 3 electron regions, is going to be trig planar again. But the molecular geometry, if we take our trig planar and we just remove one of the atoms, because again, the lone pair kind of takes up the space of an atom, a little more actually, but we don't count it in the molecular geometry. So we again get bent. But because this is a bent shape, right? If we took linear and we just bent it, that's what we're getting. But it's not the same as the other bent that we had before. The other bent was based off the tetrahedral electron geometry. This is based off of the trigonal planar electron geometry. So we get bent, but it's not the same bent. So this is going to have a less than 120 degree bond angle, not less than 109.5, okay? So we have to know our electron geometry first, and then we can figure out the molecular geometry and the bond angles from that, okay? So that's basically that. And then let's see here. Let's do, I think actually I have room right now. So let me just draw kind of a line here because I want to keep together the electron geometries. But now let's do something like CO2. We have C double bonded to an O and another O. How many electron regions do we have on this? Well, there's just that atom bonded over there and this atom bonded over there. There's no lone pairs on the carbon. It doesn't matter if it's a double bond or a single bond or a triple bond. There's just an atom bonded there and an atom bonded there and no lone pairs. So there's only 2 electron regions. So what's the furthest that 2 things can get away from each other? Well, basically a straight line, right? So if your fists were negatively charged, they're going to try to get away from each other. And if you go this way, they're getting closer. If you go the other way, they're getting closer, right? They want to be as far away from each other as possible. And so in this case, and by the way, there was no lone pairs here. And so the electron geometry is going to be linear. This is the only time that we get the linear geometry in these types of cases here. There actually are other ones, but we'll get there later. The point is, there are no lone pairs, and all the electron regions are atoms. There's only 2 of them, so we get linear. And so, of course, linear, and also, by the way, the molecular geometry is also linear because all 2 electron regions are atoms bonded to the central atom. And so this is going to be 180 degrees. That's 180 degrees. And then, of course, also, if we only have 2 atoms bonded to each other, there's no central atom, but like if we look at like a O2, or let's do Cl2. If we have a chlorine bonded to another chlorine, this is getting a little ugly here, but there's only 2 atoms bonded to each other. So there really is no central atom. And if you only have 2 points and you connect them, that's a straight line. So we could also call that linear, but there really isn't a bond angle because it's just 2 atoms bonded to each other. Okay, guys? So this is kind of an intro to molecular and electron geometry. There are things for expanded octet, which I can do another video on, but I'm going to wrap this up here. So again, if this helped you guys, please give a like, follow, share, save, so you can review it again. And please consider supporting me over here, and I'll see you guys in the next one.